but very difficult to measure right now. So the fact that when we say something has come from billion light years away, that means the billion light years it was traveling, there are these galaxies and structures of galaxies which it was interacting with, so it has to bend. But the change in bending coefficient is so tiny right now. It is there in the signal, our detectors are not good enough. And maybe when we go to the space, the LISA mission would have, the technical word is signal to noise ratio. The signal to noise ratio of bending of gravitational waves has to be high enough, and LISA can probably see that.
So how you said like the gravitational waves can hit the Earth, do those waves have any like negative effects in any way?
No, it's actually one of the problems I give in my graduate class, that if collision of two black holes happen at the edge of solar system, can humanity survive? And the answer is yes, it can actually sustain, because the impact of gravitational waves, even if it's such a highly energetic event, it cannot break the bonds, electromagnetic bonds that are there. I mean, we would know a gravitational wave has passed by and it would have other serious effects, like a black hole coming towards us. But the waves by itself will not have. So by and large, the whole biological evolution has had no impact of gravitational waves coming from cosmos.
You started out by talking about the dark matter and dark energy and didn't come back to that. So I'm wondering how or how much do the gravitational waves tell us about the dark matter and dark energy?
Yeah, and I apologize on not mentioning on that part, but there are two things we were able to do. When we measured the light and gravitational waves from the same event, we were able to independently tell how much the universe has expanded from this instance when the light came to the point it arrived. So that is measured as Hubble's constant. Now there is this big debate on whether the Hubble constant is, what is the exact value of it, because two different techniques don't agree. Gravitational waves offers us a third independent way to measure how much the universe has expanded. How much the universe has expanded tells us something about the nature of dark energy. That's one. The case of dark matter is this, the black holes that I mentioned that have formed in ways that we don't estimate stars to have formed, could mean that there is a primordial population of black holes that had formed very early in the universe. And what we are seeing is some sort of a tail distribution of the black holes. Those black holes may not have been formed, so we don't know if any of the black holes that LIGO see are baryonic matters. And we assume they are made out of regular stars stuff, but we don't know if there is a separate function to make them. And that's one way we are able to probe dark matter in the universe.
Sorry if my question isn't very scientific sounding, but when stuff gets sucked into black holes, what do we know about what happens to it? And if we don't know, what research is being done to find out?
No, we do know what happens when something gets sucked into black holes. We see light of gas, we see gas around black holes very often, and we see how the gas is interacting with the event horizon. I don't have the pretty picture of the event horizon team, but they took a picture of one of the galaxies, also our center of our own galaxy. You can see how the light is bending from gas that is accreting around the black hole. What we don't know what happens, of course, when it goes inside. One simple thing is we know it grows in size, right? So if you put 10 kilograms, the black hole generally gains about 9 kilograms. In a kilogram, it would emit away because of radiation or something. But it does grow in size because of gas. In fact, a lot of early black holes must have grown because of gas being accreted on it. So that happens. But specifically, I don't know what would happen to the object in it.
Any more questions? Okay.
If you mentioned that the gravitational wave gives you a different value or a new value to Hubble's constant, did it confirm either of the other two methods, or is it
It's
yet
still
a
too
third?
broad.
I'm sorry?
It's still too broad, the Hubble constant error bar. One of the things which I have been working on is if the universe has a certain way to not make stars beyond a particular size, or black holes, sorry, beyond a particular size, and that limit is around 50 solar mass. So what happens is, if you start seeing black holes that are bigger than 50 solar mass, the way we are very much inferring the mass of the black hole assumes a certain cosmology in it, because we need to know how much the waves have stretched. And so if we reverse the logic and say that there is a known astrophysical population, and yet we always see a more massive black hole, that means we can start learning something about the Hubble's constant independently, just from what the composition of black holes are. And that is something we are doing. It's just like right now, the field is still at its infancy. So the way I see LIGO is the same way as COBE was for cosmic microwave background. The goal of LIGO was that gravitational waves exist. I think it would require next generation instruments to measure Hubble constant well enough.
The only way a black hole can form is massive star, not a medium star or a small.
Yes, that is correct. That is.
Our sun is a medium star.
Our sun would create, yes, only a white dwarf.
That's massive.
Just massive stars, which are also rare. And that's why we don't have too many black holes. But a fun fact that I'll leave you all with is that the sounds that we just heard, every 15 minutes or so, a sound like this actually comes to Earth. And it hits all of us, every single one of us in this room. And that's just a fact that we can live peacefully with.
Let's thank our speaker.
Sorry. I think I heard you properly, and I heard you say that you weren't a fan of wormholes. Why? And how much do we scientifically know about them?
So one of my colleagues actually did that. Like if you had collision of two wormholes, what kind of gravitational waves it would emit? And actually all the way up till the merger, it looks exactly the same. It's just that the collision of two black holes creates a black hole, which is very specific. Collision of two wormholes creates something which does not have the same structure. It's a nice thing to search for. I don't deny it, but I don't know if there is a natural mechanism in, I would say, let's say, the number of ways universe knows how to make black hole is so much more than the number of ways universe knows how to make black holes. And that's why it is more likely what we see is a collision of black holes. But yeah, I'm not a fan of it.
Thank you all for coming.